In this video, I will give a proof of my theorem for non-compact rank 1 symmetric spaces and Euclidean spaces. And in the next video, I will give a proof of my theorem for compact rank 1 symmetric spaces. Let me briefly introduce the two-point homogeneous spaces. A two-point homogeneous space is a connected Riemannian manifold that satisfies every pair of 2 points with given distance are homogeneous. And it is classified by Euclidean space, compact rank 1 symmetric space, and non-compact rank 1 symmetric space. One interesting feature of two-point homogeneous space is if you consider 3 points in two-point homogeneous space, then the triangle satisfy trigonometric laws. To make trigonometric laws, we need a new angle which is different from our Riemannian angle. And my theorem is about shape optimization result for two-point homogeneous space. We consider domains bounded by two balls of given radii and with some condition on the radius of the outer ball here, and consider a Steklov-Dirichlet eigenfunction which satisfies in harmonic in the interior and Dirichlet boundary condition on the inner boundary and the Steklov boundary condition on the outer boundary. And this theorem says that the first eigenvalue has maximum value when two balls are concentric. If we consider only Euclidean spaces or non-compact rank 1 symmetric spaces, our condition on the outer ball becomes the radius is less than the infinity because the injectivity radius of the ambient space is infinity. However, if we consider compact rank 1 symmetric spaces, for example, sphere, then our condition becomes the outer ball is included in a hemisphere. And our proof is motivated from the first eigenfunction in an annulus. If we consider ambient space as three-dimensional Euclidean space, then we can compute the first eigenfunction of the concentric annulus, and it is computed by -1/r plus some constant. Here, small r is the distance from the center of the two balls. And then this -1/r is the gravitational potential function in R3. So it reminds me of Newton's shared theorem. Let me give you more details about this motivation in the end of my talk. So as in the three-dimensional Euclidean space, we can compute the first eigenfunction in an annulus in two-point homogeneous space. We use separation of variables, and we can show that the first eigenfunction can be computed by a real valued function A composite R sub C, and here R sub C is the distance from the center of the two poles in the ambient manifold, and a real valued function A is computed by the integral of 1 over omega t from R1 to R, and here the omega t is the density function of our ambient space. We note that the density function of two-point homogeneous space is a radial function. So I defined the density function omega in the non-negative real numbers. And one more thing I want to notice that our first eigenfunction vanishes on the inner boundary because since the distance from C to a point in the inner boundary is R1, so our first function on the inner boundary has 0 value. Now we use the first eigenfunction in the annulus to estimate the first eigenvalue of an eccentric annulus, which is B2 prime minus the closure of B1. We have variational characterization of the first eigenvalue of an eccentric annulus, and it is stated as follows. We note that the conditions of the test functions. Here, the test function satisfies 0 value on boundary B1, and our first eigenfunction in the annulus also satisfies the vanishing condition on the inner boundary. So our first eigenfunction in concentric annulus is also the test function for the first eigenvalue of an eccentric annulus, and we can substitute our first eigenfunction into this Rayleigh quotient. Then we obtain an upper bound of the first eigenvalue as follows, and also we can substitute our first eigenfunction into the Rayleigh quotient of the first eigenvalue of the concentric annulus. Then if we substitute into the Rayleigh quotient, then that Rayleigh quotient has value sigma 1, the first eigenvalue of the concentric annulus. So by comparing two Rayleigh quotients, we can compare the two first eigenvalues and we can show that the concentric annulus has maximal eigenvalue. So these two inequalities comes from the comparing two numerators of the two Rayleigh quotients and comparing two denominators of the two Rayleigh quotients. And these two inequalities are the goals of the step 3 and 4. And to compare these two integrals, we note that the two integrands are same. So the only difference comes from the two domains. So we only need to consider the value of the integrands in the different set of two domains, which is B and B prime. So if the ambient space is Euclidean space or non-compact rank-1 symmetric space, then the density function omega r is increasing function in R. So since we can compute the magnitude of the gradient of A composite, the distance function from C is computed by 1 over the density function. And we note that the distance from C to a point in B is less than R2, but the distance from C to a point in B prime is bigger than R2. So our magnitude has bigger value in B than those in B prime. Since the region B and region B prime has same volume, because B prime and B has same volume. So using this relation, we can obtain our desired inequality. So in this proof, we used the density function is an increasing function, but however, if ambient space is compact rank 1 symmetric space, the density function is no longer increasing if R is bigger than the half of the injectivity radius. So our previous argument cannot apply to our theorem for compact rank 1 symmetric spaces. So we need more delicate argument, and this argument will be explained in the last video. The step four is about comparing two denominators of the two Rayleigh quotients. And it is one of the most modifications of Centenam and Verma's proof. They considered the parameterization of the boundary of B2 and boundary of B2 prime, and then transform this integral into some identity using hypergeometric functions, and then using power series form of the hypergeometric function, they compare these two integrals. Instead of their analytic proof, we give a geometric proof, and our method is applicable to two-point homogeneous space, not only for Euclidean space. To begin with, we consider a function defined in the outer ball B2 prime, which assigns to a point X in B2 prime to a integral of the square of A composite, the distance function from X over boundary of B2 prime. Then the gradient of our function at X becomes a tangent vector at X. In the following proposition, we compute the gradient of our function at X. And we show that it is computed by minus a positive function G at X times a direction from X to the center of the outer ball C prime. So the gradient becomes a tangent vector which has direction from X opposite to C prime. And the following inequalities is about the minimum point of this function, and this says that C prime, the center of the outer ball, is the minimum point of our function. And these inequalities follows from our computation of the gradient, because using the identity, our gradient field is depicted as in the picture. Since we know that the gradient of a function at some point is the direction of steepest ascent of a function at the given point. So the function has minimum value at C prime, and this gives the proof of the inequality in the proposition. So if we have that inequality, using this identity, which is obtained from the fact that the C is the center of the ball P2, then we obtain the inequality in the step 4. So the proof of the step 4 is finished. So our goal is computing the gradient of our function, and to compute that gradient, we give some definitions. First, we define an angle function which is defined in the boundary of the outer ball, and it is the angle at P of the triangle XPC prime. And we denote the direction from X toward P by the vector V sub X at P. And also we define a projection map pi sub X, which maps the unit tangent vector at X to the intersection of the geodesic ray from X with that direction and the boundary of the outer ball. So our infinitesimal area of the boundary of the outer ball is computed by the solid angle times the density function divided by cosine lambda sub X. And this formula is obtained by using divergence theorem, but we omit the proof in this talk. Now we compute the negative gradient of our function, and since minus gradient of the integrand becomes 2 times a composite r sub x divided by the density function times minus gradient of the distance function. Here we use the derivative of a in r is 1 over omega r. And then we can show that the minus gradient of the radial distance function is a direction from x, and also we use on the infinitesimal area formula, then we obtain the second identity. And to compute this integral, let me give some definitions. And given a point P in the boundary of the outer ball, we define small p sub s in the unit tangent sphere at X. And it is defined by projection map from X, and it satisfies that the image of the projection map, projection map at small p sub s is P. Also, in a similar way, we can define small c sub s prime from the point C prime, the center of the outer ball. And then we define small p sub s bar, which is a point in a plane spanned by small p sub s and small c sub s prime, and it is the symmetric point of p sub s with respect to the line passing through x and small c sub s prime. And then we define minus small c sub s by the antipodal point of small p sub s, and we define minus small p sub s bar by the antipodal of the small p sub s bar. And then we define p bar minus p and minus p bar by the images of the projection map of these 3 points. And using trigonometric laws, then we can show that the distance from x to p is bigger than the distance from x to minus p. In addition, we can show that the angle lambda x at p is equal to the angle lambda x at minus p. So if we consider the integrand at small p sub s and minus small p sub s, then the magnitude of the integrand at small p sub s is bigger than the magnitude of the integrand at minus small p sub s. And then if we consider the other 2 points, and then we obtain the sum of the integrands at these 4 points becomes a vector that's starting from x toward the c prime. So our integral becomes a vector starting from x toward the c prime. So we compute minus gradient of our function becomes a vector starting from x toward c prime, and this gives it finishes our proof of the proposition, proof of identity in the proposition. And this argument of the proof comes from the proof of Newton's shell theorem. Newton's shell theorem says that gravitational force from spherical shell acting on an object inside is 0. So if ambient space is 3-dimensional Euclidean space, then the density function becomes r squared, and so this integrand becomes gravitational force from from spherical shell acting on x. Therefore, this formula says a generalization of Newton's shell theorem for 2-point homogeneous space. And the proof is very similar as in the proof of the proposition. Using infinitesimal area formula, and then our left-hand side becomes integral of the direction from x divided by cosine lambda sub x composite projection at x over the unit sphere. And since we can show that the cosine lambda sub x at small p sub s is equal to the cosine lambda sub x and minus p sub s. So, so, so the sum of this integrand at these 2 points becomes 0. So our integral becomes 0, and this finishes our proof of our corollary. Thank you for watching this video, and see you in the next video.